We're going to continue on here, chapter 5. So we started talking about obviously balancing equations. And remember that when we do balance equations, it is only those coefficients up in front that we change. Again, we never change any other number except, again, the guys that do come up in front. The goal is obviously to end up with the same amount of elements on both sides of the arrow. Conservation of mass, we don't lose any elements along the way. Nothing's changed any other elements. So you should start with and end with the same number of elements. As we talked about, you can make a nice, not ice table, you can make a table there to help you with the balancing. It kind of will organize it for you a little bit and maybe point you in the right direction in terms of where you should start. Remember, you kind of just want to put coefficients there until everything falls into place. Really, there's only kind of two main things when it's all said and done. All the coefficients have to be whole numbers, and they do, again, have to be the simplest set of whole numbers. So as we talked about, I think last time as well, if you went through this guy and you balanced everybody out with like a 4, a 2, and a 2, you obviously could go through again and reduce that down. And you should reduce it down to like 2a plus b goes to c. And that would be, again, the properly balanced equation. We also saw a couple of situations or so where it's very common that, in order to balance an equation, you might need to use a fraction to do so. And you definitely could use a fraction to balance an equation. The simple rule for the fraction is usually the number on top is the number you need, and the number on the bottom should match the subscript that's there. And you can use it to balance the equation, but you do need to sort of get rid of the fraction at the end there to have it properly balanced. So you got to go through and kind of multiply everybody by the denominator. And again, that should give you all whole numbers and a properly balanced equation. We also saw some equations there where you have a lot of sort of polyatomic ions involved. And again, a lot of times when you do have that situation, polyatomic ions on both sides, it's a lot of times very much easier to sort of keep them together and like balance them as like whole units of, I got 3 phosphates on this side and 1 on this side, and kind of balance it that way. And when you kind of take that approach, it usually will happen a little bit quicker for you. And, as you balance, say, the first polyatomic ion, whatever is sort of attached to it, then that's where you should go next to balance that guy. And then it'll kind of move you through the equation. And usually what will happen again is pretty much everything will sort of fall into place at that point. Any questions on the balancing part of it? Now, we also then got into the idea of sort of classifying reactions. And as we sort of touched upon a little bit there towards the end, there are a lot of times multiple ways you could look at one reaction and sort of classify it, sort of depending on what you're looking at. But overall, there's really sort of two big classifications and terms of types of reactions for which more specific classifications can fall underneath. One big category that we started talking about there last time is redox reactions. And redox reactions basically involve gaining and losing electrons. So oxidation and reduction reactions. Oxidation, one definition, and usually the definition we sort of look at in general chemistry is the loss of electrons, while reduction means that somebody has gained electrons. There are a couple other definitions we'll look at in just a second, but for the most part in general chemistry, those are the two that you mainly sort of look at. Remember, we talked about, you could remember that Leo the lion goes grr, or oil rig. Either one of those will sort of work. We also said that, basically you could kind of follow the change in truly what's known as oxidation state, but you could kind of think of it as the charge of each element as you go from kind of left-hand side of the arrow to the right-hand side of the arrow. And you could just use a basic number line to help you identify sort of what is happening. When things do lose electrons, they obviously have more protons than electrons, so they become more positive. So if you see an element on the left-hand side to the right-hand side, the oxidation state or the charge becoming kind of more positive, that substance is going through oxidation. Opposite is true, obviously, if you gain electrons, you're becoming more negative as you have more electrons than protons. So if you look at an element on the left-hand side of the arrow and the element on the right-hand side of the arrow, and you see its oxidation state or charge sort of becoming more negative, that guy is going through reduction. So it's sort of an easy way you can just kind of follow the charge. And again, truly, it's really what's known as oxidation state, but we'll call it a charge here. So as we'll talk about here in just a second, under sort of the big umbrella of redox reactions, there's sort of more specific ways you can classify reactions, you know, kind of depending on what you're looking at. The other really big class of reactions fall under the double displacement sort of umbrella. And in a double displacement reaction, you can really recognize it because there's pretty much no other reactions that kind of are set up this way. So if you look on the reactant side and you see two things there, and both guys are pretty much ionic compounds, so like a positive and negative guy together, that is pretty much 100% of the time going to be a double displacement reaction. And essentially what always happens in this reaction, no matter what type of double displacement reaction it is really the two positive guys switch partners. So in this case, the A would end up over there with the D, and the C would end up over there with the B. And we will actually make two new ionic compounds on the other side, an A and a D. In this case, a C and a B. And as we will also see sort of under that big umbrella double displacement, we can get even more specific in terms of the type of reaction we're talking about. It may make it solid, which is referred to as a precipitation reaction. May make water, which is oftentimes happens in an acid-base reaction. So these are really the two sort of big classifications of reactions to which we could get even more specific as we go through this chapter here. Any questions on that stuff there? All right, so we talked about oxidation and reduction and the basic definition of it. We really don't run into it too much in this class, but if you ever find yourself in an organic chemistry class, I'm sorry for you. But if you do, you know, you can look at some other definitions of oxidation and reduction. Another definition of oxidation, in addition to really the main one that we look at, which is the loss of electrons, is something will gain oxygen as you go from reactants to products. So from the left-hand side to the right-hand side of the arrow, something sort of gains oxygen is another example of what an oxidation sort of means. Reduction, on the other hand, also in terms of oxygen, means pretty much the opposite. So we're going to gain electrons, and it is something that loses oxygen as you go from reactants to products. So a lot of times sort of the oxidation reduction definition involving oxygen or hydrogen is used a lot in things like organic chemistry because it involves a lot of nonmetals. So nonmetals, you don't necessarily maybe have charges and stuff like that. So looking at it, whether or not oxygen appears or hydrogen appears or doesn't, is a good way. So for example, here, if we just kind of look at this guy, that is sulfur that has a couple of oxygens there. And on the right-hand side, it obviously gains some more oxygen. So the sulfur here would actually be going through oxidation. By default, the oxygen here would be going through reduction. That was the other thing that we talked about, that they always occur together. So if something gets oxidized, something else does need to be reduced, and vice versa. And the beauty of that is, you know, if you could just at least identify one of them, then by default, the other guy is sort of the other thing that's happening. Here, if we look at the copper, this is actually copper 2 oxide, which is +2. And this is copper by itself, which has no charge. So in this case, we actually have copper, and we can actually look at like we did before, but if we didn't, we can see here that the copper actually is losing oxygen as it goes from left to right, which means that it is actually going through reduction. And obviously the hydrogen here would be the one going through the oxidation. In this particular case, because there is a metal, we could actually do what we did the last time. We see if we look at the carbon, it started at +2, which would be here. It ends at 0, which means it is moving in this direction towards the negative side, which again tells us it's going through reduction. So if you do have the metal there or a metal, it's a really good way to, you know, kind of figure it out. Hydrogen as well is also used in terms of oxidation and reduction. So if something loses hydrogen, which is usually H2, but we'll call it hydrogen, as it goes from reactants to products. That's the kind of third definition of something going through oxidation. And if somebody gains hydrogen from reactants to products, is sort of the third definition of a reduction. And again, really more in an organic type class, you really see a lot of that. For us, it really is these definitions of electrons that we talked about earlier that's probably more applicable to what we will see in general chemistry. Any questions on that there? And that's what this is talking about, the hydrogen. So again, in this case, we see that carbon had some hydrogen there, but ended up with no hydrogen on that side. So it lost hydrogen, which means it went through oxidation. You could also see that the carbon also gained oxygen, which is a definition, obviously, of oxidation as well. So again, you can choose any way to look at it, and you'll have that guy there. Obviously, that means that this guy is going through reduction. Any questions about redox reaction, sort of the electron transfer part of it there? I think we also maybe talked about reducing agent and oxidizing agents, did we? Yes. So remember that the reducing agent is the substance that gets oxidized, and the oxidizing agent is the substance that gets reduced. So kind of opposite of the name when you talk about sort of the agents. All right, so now what we're going to talk about is really these sort of three driving forces for reactions. And now that we sort of have the big idea of how these reactions are classified, we're going to talk more specifically, more specific classifications that occur. As I mentioned last time, this is really the three reasons why a reaction takes place. It either wants to form a solid, it wants to form water, or it wants some type of electron being transferred. And we commonly see the first two here under the umbrella of double displacement reactions is commonly where, you know, those things kind of take place. The last one here we commonly see under redox reactions is basically where that guy takes place. So, you know, if you ever wonder, you know, really why this reaction takes place, is really one of these three things is going to happen. Either you're going to make a solid, make water, or there's some type of electrons being transferred. So we're first going to look at some more specific ways of classifying redox reactions here. So let's take a look at those. So the first type of classification that, again, really does fall under the redox umbrella is what is referred to as a synthesis or combination reaction. And I think we might have touched upon it the other day. But really in the synthesis or combination reaction, the general formula of what you got going on is essentially you take two things and you make one thing. So kind of two things together, hence the name combination. You're just going to combo those two things together to make one thing. And that's your classic setup for a combination or synthesis. So here's the formation of water. Two things make one thing, and that is going to be a synthesis or combination reaction. This is our sodium and our chlorine. Two things make one thing. And again, that is a classic setup for a synthesis or combination reaction. Now, when you look at these reactions, probably in most cases, people would classify these reactions as either a synthesis or combination reaction. If we delve a little bit deeper into sort of what is going on in each of these reactions, we will also sort of see the redox connection. Remember that hydrogen all by itself has really no charge. Oxygen all by itself has no charge. Water you can think of as this guy being +1 and oxygen being -2 is what's happening here. And when we look at what's really happening, if we look at the hydrogen, it starts at 0 and ends at +1. And we do see that the hydrogen is going more positive. So it is going through oxidation. And we look at the oxygen, it started at 0 and ends at -2, which means it's becoming more negative. So it's going through reduction. So although most people would classify this as a combination or synthesis reaction, it is still really those electrons being transferred here in this particular case, and it's a redox reaction that's happening. So again, as I talked about, the redox is the big umbrella for which you can get really specific and call it a combination or synthesis reactions going on. I think we might have looked at this one last time, which was the sodium and the chlorine. Same deal here. 0 here, +1 and -1. So again, the sodium going from 0 to +1, becoming more positive, going through oxidation, like we would expect since it is a metal. The chlorine going from 0 to -1, becoming more negative and going through reduction. So again, even the bottom one there is also really a redox reaction that's happening. So one sort of subclassification of a redox reaction is a synthesis or combination reaction. And the way, again, you can very easily recognize it, left-hand side, a couple of things, right-hand side, one thing, everybody put together, basically. Any questions on synthesis or combination there? Now, sort of the reverse or opposite of a combination reaction is a decomposition reaction. This is also a redox reaction. So this is also under the big classification of redox. So if you think about synthesis or combination as putting it together, decomposition is basically breaking it apart. So just kind of the opposite. You start with one thing and you make a couple of things or more on the other side. So if we took an electrical current over water, I don't think they do that here, but you run electrical current over that and you could split water into hydrogen gas and oxygen gas. Again, one thing makes two things, decomposition. Little mercury 2 oxide over here with some heat will give us some liquid mercury and some oxygen. Again, two things, one thing making two things, classic decomposition reaction. And again, it is still really a redox reaction happening here. So if we look at this, that is +2 for our mercury. That is -2, which is really the charge on the oxygen in that case. That is 0. And that is 0 in that case as well. So what we see happening here is if we look at the mercury, it started at +2 and ended at 0, which means it is moving in that direction, becoming more negative. So it's actually the mercury here that is being reduced. The oxygen started at -2, which would be over here, and ends at 0, which means it is moving in that direction, becoming more positive. And it's actually the oxygen here that is going through oxidation in this particular case. Thank you. So again here, decomposition, a more specific way of classifying a redox reaction. But ultimately here it is that transfer of electrons, the redox reaction that is ultimately taking place. But like I said before, probably 9 times out of 10 or even more, if you or somebody was asked to classify those reactions, they most likely would classify it as a decomposition reaction using the more specific sort of classification of it. Any questions on that one there? Another redox sort of reaction and a more specific classification of it is a single displacement or single replacement, sometimes people call it, reaction. This again does fall under the same umbrella of redox reactions. And the general setup of this reaction is you have something and another something. So you have something that is by itself uncombined, and this, for example, could be a metal, and you have an ionic compound, basically. So when you have a metal that is uncombined and by itself, it really has no charge or oxidation state to begin with. But when metals do gain charges, do they typically become positive or negative charged? They do. So what happens in this case is, although it doesn't have a charge at this point, it will come in and actually try to kick out the positive guy. When it does, it's at that point that it will actually gain a positive charge, and we will form a new ionic compound. And what will happen to the guy that was originally there, B, he will come out by himself and actually come out by himself and will end up with no charge that occurs in this case. And this is what is known as a single replacement. And it is recognized just like this. You got one thing by itself plus an ionic compound, pretty safe bet you got a single replacement reaction happening. And that's what we see here. The zinc, which has no charge in that situation, will come in and kick out the hydrogen, which is positively charged. When the hydrogen comes out by itself, whenever you kick out hydrogen in a reaction like this, you always form hydrogen gas. So if you ever did this, or maybe you have done this in lab or will again or some point, if you do this reaction, you'll see a whole bunch of little bubbles start to form in the test tube, for example, and the piece of metal will start to kind of dissolve and go away. And a lot of bubbles will form, and that's the hydrogen gas that's actually occurring. And then obviously the zinc gains the charge over here, becomes +2, and we'll make an ionic compound there with the chlorine or the chloride. So this is a single replacement reaction. If we follow sort of what is happening with the charges over here, we could also see that it again is also a redox reaction. In this case, the zinc, if we look at the zinc, it is starting at 0 and ending at +2, which means it is becoming more oxidized. And it's actually the hydrogen here that starts at +1 and ends at 0 because it's hydrogen gas by itself. Actually ends at 0 heading in this direction. So it's actually the hydrogen here on the left there is going through reduction. How about the chlorine on each side? Is anything happening to it? It is not. It's what we call a spectator ion. It's just kind of hanging out, watching, not really doing much. It's just there to balance out the charge. There's really nothing happening here with it. So it is, as you can see, also obviously a redox reaction, a single replacement. You could also do this in a situation where, again, you have an ionic compound, but you're going to start with a nonmetal. And a very similar reaction will happen. A nonmetal by itself has no charge, but when a nonmetal does gain a charge, it is negative. So what happens in this case is it will actually go in and kick out the negative guy, not the positive guy. And again, at that point, that is when it will gain a charge and it will make a new ionic compound. And the negative guy that gets kicked out will come out and basically be by itself. So if you took something like chlorine here and a little sodium bromide, this is chlorine by itself, no charge. This is an ionic compound. So that is a classic setup of a single replacement reaction. The chlorine will come in and kick out the bromine. At that point, the chlorine will gain its -1 charge and make sodium chloride, which is our ionic compound. The bromine will come out, and when bromine comes out by itself, it's a diatomic molecule and will make Br2. And again, this little balancing would be good since it's chemistry, I suppose. There you go. This again is a single replacement reaction. Usually involves the halogens a lot. Group 7 does that a lot with each other. By the way, reactivity increases as you go up group 7. So chlorine is more reactive than bromine. Any question on those reactions? Yeah. Yeah, so double displacement in this one, they're similar looking, but there actually is a difference. In double displacement, as we will see, you will be starting with 2 ionic compounds. In a single replacement, you'll just have 1. So like in this case, up here, we really only had 1 ionic compound, and here only 1 ionic compound and something by itself. And that's really how you can recognize it as a single replacement. 100% of the time when we get to a double displacement, you're going to always be starting with 2 things that are ionic. And that's the way I grammar. Other questions? Yeah. Why does Josh, why does it 2 come out over here? Yeah, so if you remember when we talked about certain elements that are by themselves, they come as diatomic molecules. So like hydrogen, nitrogen, oxygen, and pretty much everybody in group 7 there, the fluorine, the chlorine, the bromine, when this gets kicked out, just like above, actually up here, when hydrogen gets kicked out, they become basically their elemental form, and those guys just happen to be 2s. That's how they come. So that's why it ends up over there. What's that? It doesn't. There's actually still 2 chlorines over here when we balance the equation. It just happens. So each of these chlorines, for example, they're together. As this process occurs, kind of it breaks, and you get two of these guys, which is represented over here with the two that they have a charge. Again, on the left-hand side, they don't have a charge, but through the process of sort of gaining and losing electrons, in this case, they separate out, and obviously the chlorine here gains an electron, each of them, and that's why we end up with actually two Cl minuses. Other questions? So one last thing on this that's really important is the only way that this reaction actually takes place is if whatever is coming in needs to be more reactive than what it's replacing. So for example here, whatever is sort of coming in needs to be more reactive than what it is replacing. So this reaction does take place, the chlorine and the bromine, and that means that the chlorine is actually more reactive than the bromine. If you switch it around and try bromine replacing chlorine, it actually would not work. Bless you. In the case up here, the zinc is more reactive than hydrogen. If you did that exact same reaction with copper instead of zinc, when the copper would come in here, it is actually less reactive, and you actually would get no reaction that would take place. So it has to be more reactive than when it's replaced in order for this reaction to take place. If it is not, then you actually would not see the reaction take place. Years ago, we used to do an experiment with old pennies versus new pennies. Yes. And old pennies are copper. Yes. New pennies are copper on the outside, kind of zinc in the middle part of it. And, you know, we could tell which one's old or new. We'd file it open, put in some hydrochloric acid. Old penny, still there. New penny, the inside basically goes away because all that zinc will react with the hydrochloric acid. So there is what is referred to as an activity series of metals that you might sometimes come across, and basically the activity series of metals is really a lot of times just a list of metals. So you'll see a lot of metals listed, and somewhere in the middle is like hydrogen. You'll see a bunch of sort of elements listed underneath, and this is what's sometimes referred to as an activity series. And basically how an activity series works, if you ever see one in your book or maybe in lab, is pretty much anything higher on the list is more reactive than anything lower on the list. So anybody higher is more reactive than lower, and vice versa, obviously. So if you look on this, if you'd find zinc up here, which means zinc is more reactive than hydrogen, and we would see that reaction take place, you would find copper kind of down here is less reactive, and it actually would not take place. So sometimes that's a way you can look at a list like that and determine whether or not you would expect this reaction to take place, or if you're in the lab and you do it and you actually see the reaction take place, then you know whatever's coming in is more reactive than what is replacing. The non-metal sort of reactivity, I'll be right with you, non-metal reactivity really goes with the halogens, and reactivity actually increases in group 7 as you go up. So chlorine will replace bromine, but again, if you switch it around and try to use bromine to replace chlorine, will not take place because bromine is less reactive than chlorine. Yes, question? Okay, yeah. Yeah, so, you know, for the most part, the non-metal sort of aspect of this usually will involve that group 7. And again, reactivity does increase going up. So some people will use that as like an activity series for the non-metals. And again, for metals, you know, it's a pretty big list. So sometimes you'll find it somewhere there. For our purposes here, if you're given a reaction like that and you maybe have to write the thing at the end, I'll probably just say, just assume it's going to occur. Okay. Was there a different question, or did I get it? Yeah. Okay, so single replacements, again, really redox reactions. And we're basically having one guy come in and kicking somebody else out. So those sort of fall under the redox umbrella. We're now going to talk about some reactions that fall under those double displacement side. And again, as we were just talking about, very much the way you can recognize it is you definitely will 100% of the time have two ionic compounds going on here. And again, it's really these two positive guys. They really just switch partners. And again, we always will then, in this case, make 2 new ionic compounds on the other side. Now, when this reaction takes place, again, that is much like redox, the big classification of reactions. When one of these reactions take place, very commonly, one of the guys on the right-hand side will sometimes make a solid, which is sometimes referred to as a precipitate, PPT. And that is why one more specific way to classify a double displacement reaction is as a precipitation reaction. And then a precipitation reaction, essentially you take 2 solutions, mix them together, and you get a solid that forms. The solid does not have to be sort of a rock hard solid. When you make a precipitate, it can be just, cloudiness occurs, some stuff floating there that wasn't there before. Sometimes people think the solid has to be like rock hard into the bottom. And that's what we see here. This is potassium chromate. That is a positive and negative guy. This is barium nitrate, which is also a positive and negative guy. And what ultimately is happening here is the positive potassium is going to hook up with the nitrate, which is the negative guy. The barium, which is the other positive guy, will then switch partners and hook up with the chromate on the other side. It's really important, if you perhaps are not given this side and you want to sort of write what you're going to get on the other side, that you actually do it in the proper order. And what I mean by that is you should write the equations first, the formulas first, and then balance it. Very common, people try to do both at once and end up with the wrong formulas. What I mean by that is if we were to take this guy apart, we basically get a couple of things here. The basic unit of this guy is a potassium ion and a chromate ion. So those are the basic 2 units that basically make up the first guy. The basic 2 units that make up the second guy here is a barium ion and a nitrate ion, which is NO3 minus. So when we get to the formulas on the other side, we want to do it just like a nomenclature. We're basically taking both of these guys and we're putting them together, which is basically +1 and -1. And that is why the formula over here is KNO3, not like K2 parentheses NO3 2 and some crazy formula like that. When we put this guy together, which is basically a +2 with a -2 over here, we just need one of each, which again is why the formula over here is BaCrO4. Once you get the formulas, then you could go back and balance with coefficients like we see here to get the same amount on each side. So it's a very common when people would do something like this, they would go, oh, I have like K2, NO3, 2, and that is my formula because I want to try to balance it and write the formula. So you don't want to do those things. You want to make sure you get the correct formula down first, then go back and change the coefficients if you're asked to obviously predict what goes on the other side. A lot of times in labs, they ask you to do that, like predict what's on the other side and all kind of stuff. Any questions on that there? But this is a double displacement reaction. We make, again, 2 new ionic compounds. And again, that formation of a solid there, which is why it's more specifically called a precipitation reaction that's actually going on here. Any questions on that there? So what is happening in this reaction? Again, we basically see that both of the ions have basically switched partners, the positive guys, and they end up in the opposite location, which is your classically done double displacement reaction. So for example, if you took something like silver nitrate plus a little bit of sodium chloride here, when I look at this, again, I know it's a double displacement reaction because positive, negative, positive, and negative. So I know they're going to switch partners here. And we will produce silver chloride, which is a white solid that you get when that comes together, and a little sodium nitrate at this particular case. So these are both solutions here. So if we had a beaker and we took some silver nitrate and we took some sodium chloride and dumped it in here, these are really sort of solutions, and when they go into that beaker, they are basically going to break apart. And ultimately what is happening, this is what obviously we refer to as the molecular equation. What's really happening though, when we dump them into that beaker, is the silver nitrate will not stay together. It's what's referred to as a strong electrolyte, which means it's going to break apart. And what you will get with that is basically some silver ions that are floating around. So as you do that, you'll get some silver ions that are floating around in there. You'll get some nitrate ions that are floating around. And from the sodium chloride, when you do it, you will get some sodium ions that are floating around. And you will get some chloride ions that will float around. And what happens in this case, pop my chloride in here, is the silver and the chloride that when they see each other as they're floating around, they're actually really attracted to each other, and they will come together and really bond, and they will actually drop out a solution, if you will. It won't look like this. It'll look more like a white solid. Probably will still be floating around all the white. It'll just kind of look cloudy usually. And you'll get the silver chloride that will kind of come out of solution. Because it kind of came out of solution, it's no longer kind of floating around. We actually don't break it apart. We just keep it together like it is in the actual sort of beaker. And then the sodium ion and the nitrate ions, as you can see in the picture, are still there floating around in the solution. And those guys are just floating around. As I run out of room over here, we'll go there. And this is what is sometimes referred to as a total ionic equation. And this is describing what's really truly happening when you kind of dump those things into the beaker. You get the silver ion, the nitrate, the sodium and chloride ions floating around. There's an attraction that occurs between the silver and the chloride that will make it come out of solution as a solid. And you still have the sodium and nitrate ions basically floating around. If we look at this, we can see ions on both sides of that equation that look exactly the same. That is the nitrate ion on the left and the nitrate ion on the right, and the sodium ion on the right and the sodium ion on the left. Those guys look exactly the same. And what those guys are referred to as spectator ions, which are these guys in my picture up here that are still floating around freely in the solution at this point. If you are a spectator, you are doing what? You're watching, right? And that is essentially what these guys are doing. Although they're there just to balance out the charge, but they are really not doing anything to form any type of product. They're just kind of hanging out and watching. Now, what we typically do with spectator ions is we get rid of them in this formula. And what we're left with is a third type of formula, which is very commonly written a lot, which is the silver ion in this case and the chloride ion will come together to make silver chloride. And this is what is sometimes referred to as the net ionic equation. And what the net ionic equation basically tells you is when you dump both of those things together, in this particular example, the silver nitrate with the sodium chloride into that beaker, what is really happening is the silver from the silver nitrate going and finding the chloride from the sodium chloride, and those guys are going to come together to make the solid that is formed as a result of this reaction. So sometimes when we look at equations, a lot of times some people will talk about what is a net ionic equation happening. And really that's the equation that gets rid of everything else and cuts down to the chase that this is actually what is happening in this reaction. And what we see that is actually happening is the formation of a solid, right? Which is one of those driving forces for why reactions take place. And this one, we put two solutions together, we get that solid that forms, and ultimately that is sort of what is happening here. Any questions on that there? So as we can see, double displacement reaction, big classification. If it results in a solid being formed, that can more specifically be classified as a precipitation reaction. How do you know if you do get a solid that forms? You could use what are referred to as solubility rules. Solubility rules tell you, when you take these two sort of ions together, would you expect a solid to form or no solid to form? So for example, things like anybody in group 1 are soluble in everything. So things like sodium, which is in group 1, or potassium here are soluble. We'll never make a solid with anything. Things that contain nitrates are soluble in everything. There's no exception. So that's why when we see silver nitrate here, it's always going to be a solution. It will never make a solid if you have nitrate in it. Some other things that have ammonium in it are soluble in everything. There's no exceptions. Things that have chloride, bromide, or iodide are soluble in everything, except there are 3 exceptions, and there are 3 exceptions, which is silver, lead, and mercury. And that is why when we put the silver and the chloride together in this case, we actually do get a solid, because it's one of the exceptions, as opposed to when we have sodium and chlorine together, that is not an exception, and those guys are always going to be soluble in each other. So we'll get into some solubility rules, I think, a little bit later on, but that's some of the general ones, popular ones that you see a lot. And again, that's how you could sort of predict whether or not, if you kind of put these things together, you would get a solid. Any questions on that there? So another reaction that does fall under the double displacement umbrella is really acid-base reactions. And in acid-base reactions, especially strong acids and strong bases, we basically get water that is being formed here. And that is, again, what we're looking for in terms of why a reaction takes place. Although this is really non-metal, it is kind of treated like an ionic compound. So that's a positive negative guy. That's a positive negative guy. And this is the acid. That is the base. And it is the H from the acid that goes and finds the OH from the base. H and OH will make water. So that is where water always comes from in this type of reaction. H plus from the acid, OH minus from the base will make water. And what the other guy is sometimes referred to is a salt. A salt is a fancy word. I'm not sure how fancy it is, but it's a fancy word for an ionic compound. And that's basically what we got going on here. It basically means an ionic compound. And as you can see, that's a positive negative guy. And that's from the positive potassium +1 going to the chloride, which is -1, to make it. So it is a double displacement reaction, but it is also more simply classified as an acid-base reaction, or is sometimes reclassified as an acid and base neutralization reaction. So what is really happening here when we dump both of those things into the beaker, much like what we talked about a second ago, if I take my hydrochloric acid, which is a strong acid, and I take my potassium hydroxide, which is a strong base, when we dump it into the beaker together, the HCl is not going to stay together because it's a strong acid. It will break apart into H+ ions and chloride ions. So you get some H+ guys floating around, you get some chloride ions floating around. When the potassium hydroxide goes for a swim, it's also strong. It will break apart into a potassium ion and a hydroxide ion. So you get a little potassium ion and hydroxide ion happening. Now, that will form water, because whenever you get pretty much H+ near OH minus, they are super attracted to each other and they're going to form water. Can you visually see that you formed water? The answer is no, you can't visually see it, right? It just looks the same basically, right? Unlike a precipitation reaction where you can visually see you made a solid, in this deal, you really can't see that you made water unless you did some other things there to help you. And what will happen is the potassium will break apart there on this side, and the chloride also floating around. As we can see here, we still have the We still have the potassium floating around and the chloride floating around. So again, the water kind of comes out of solution. And as you can see, our spectator ions, again, in this case, is potassium on both sides and the chloride on both sides. Those guys are just hanging out and floating around, really not making anything. And ultimately, if we get to the net ionic equation here, we are left with basically it's the H plus from the acid that comes together with the hydroxide from the base to make water. And that is ultimately what is happening whenever you take any strong acid and strong base together. No matter what combination of strong acid, strong base you put together, you are basically just making water, which is again why it's sometimes referred to as neutralization reactions, because they're kind of like neutralizing each other and you're left with basically water at the end of that reaction. So a more specific way to classify this, and again, in most cases, probably most people would classify this as an acid-base neutralization reaction. It can also obviously be classified under the big umbrella of double displacement reaction as well. Any questions on that there? Now, the last type of classification of a reaction is a combustion reaction. And honestly, there are two sort of definitions that people think about when we talk about combustion. I would say probably 99% of the time, if you ask somebody what is going on in a combustion reaction, they are most likely thinking of these type of reactions that we see up here on the screen. And this type of reaction, we have something that is an organic compound. And you know it's organic because it contains carbon, hydrogen, maybe oxygen in there. And if you have something that's like carbon, hydrogen, or carbon, hydrogen, oxygen, and you see on the left-hand side O2, and on the right-hand side CO2 and water, that is 100% going to be a combustion reaction, like your engine, combustion engine, like when you light a Bunsen burner, which is this reaction right here, a little bit of methane, a little bit of oxygen from the air. You guys use strikers in lab? Have you lit a Bunsen burner? Yeah, yes. Bunsen burner? Yeah, yeah. You use strikers? Yeah, yeah. So you make a spark, right? And oxygen in the air with the methane coming out makes fire and flame. A lot of organic combustion reactions do involve that, obviously, flame and heat and stuff like that. That's propane, right? In case you're cooking something, right? Or butane and those type of things. Again, very classic organic combustion is O2 on the left, CO2 and water always on the right. So, you know, if you kind of see that setup of an organic guy with O2 on the left, pretty much just write CO2 and water on the right, and you should be in good shape. You can have what is sometimes referred to as an incomplete combustion. You make like carbon monoxide instead of CO2, but most of the time it should be CO2 and water. Now, there is a more sort of generic definition of combustion reactions that some people follow, and that is a reaction where pretty much the only thing that you need to have present is O2. So that is really a very generic definition of a combustion reaction. Technically speaking, any reaction that you see that has O2 on the left-hand side is technically a combustion reaction, even though we usually think more of the organic one. Yes, sir. No, you just need to have oxygen present with some other stuff, obviously, but you know, you just see oxygen on that side. Yeah. So for example, this one that we saw earlier, this magnesium plus some oxygen makes some magnesium oxide here. And we'll do like a 2 there and a 2 there. Now, technically speaking, this could be classified as a combustion reaction because there's oxygen there. So you could classify that as combustion. We also saw earlier that that is 1 and 2 things that make one thing, which means you can technically classify this as a synthesis or combination. And if that wasn't enough classification for this one reaction, this is also, again, a redox reaction that's happening 0, 0, plus 2, minus 2. So it's a redox reaction that is occurring as well. So you can see, you know, you can get crazy with the classifications. You can look at the same one. For example, this one's a good example of that. And you could actually classify it 3 different ways. Again, I would probably argue that most people, if they looked at this reaction, would go with the synthesis and combination as probably the one, maybe combustion or redox, but technically speaking, all three of those classifications are correct for this particular type of reaction. So as we see, there are definitely multiple ways you could classify the same reaction. Sometimes it just depends on sort of what aspect you're looking at. And for us, obviously, it would be, if there was no sort of boundaries in terms of how to classify it, if you choose anyone that's technically correct, you're good. But if it's obviously a list to choose from, you want to choose the most appropriate one from the list or something like that. Any questions on ways to classify reactions? So just to summarize where everything sort of sits in terms of reactions, I got a page here. Let me just get rid of this stuff here. So again, on the redox side of big classification reactions, underneath that, you have your synthesis and our combination reaction. You have your decomposition reaction. You have your single replacement reactions. And you have really your combustion reactions. So again, the big umbrella being redox, but more specifically underneath that, you can classify a reaction one of those ways, or even multiple of those ways, depending on sort of what you're looking at. The other big umbrella is double displacement. And really underneath this umbrella, we're looking at precipitation reaction. And we're looking really at acid and base reactions. And between both of those big classifications and more specific classifications, over here, we take care of the idea of transferring electrons. And really over on the right-hand side, we take place of making a solid and making water, which again is our sort of 1, 2, and 3 reasons why reactions take place. Any questions on classifying reactions? So clearly, if you're given a reaction or equation, you need to be able to balance it. You need to be able to classify as a type of reaction one of these ways. And you should have a general understanding of, if you just look at an equation, what the look should be. Again, for synthesis and combination, it's basically 2 things make 1. Decomposition is the opposite. 1 thing makes multiple things. Single replacement, something by itself plus an ionic compound coming in. Combustion, involving oxygen pretty much. Precipitation, and these guys really are the same all the way across, 2 ionic compounds basically on this side of the arrow. So those are the things you want to look at when you kind of look at an equation, and just kind of think of the generic way those guys come together. And that also can obviously help you identify a little bit quicker in terms of what's happening. So the next thing we're going to talk about then is, if there's no questions, yes. Yeah. So I say technically yes, but I don't know how much of that I'm going to ask you to do. Sometimes they do a lot of that in labs and stuff like that, when they get into that. But technically you should, but I would say more probably for our purposes, knowing if you have the equation, just looking at what type of reaction it is. So I would say the only one maybe where predicting would maybe come into play would be maybe like a double displacement. That's not too bad. It's basically just putting ionic compounds together. Obviously, decomposition might be a little hard if you don't really understand, what might form on the other side, because a lot of times in decomposition reactions, you do generate a lot of gases and stuff like that. So sometimes that's hard. So I would say maybe the only places you might have to predict something would be like this type of one, where it's just a simple, these 2 guys are just going to switch partners, right? And, put it together correctly on their side. Other questions? All right, so that. All right, so next thing we're gonna talk about is molar mass and Avogadro's number. And where we're kind of leading to in this chapter is kind of taking equations. We're going to talk about some calculations here and kind of putting them together to help us understand how to figure out things like, how much product I would make in a reaction and so forth. So the first thing that will help us get there is the idea of a mole, not the furry guy, but a mole is basically a unit in chemistry which does represent a certain amount. So in life, we have a lot of words that we say that does represent kind of like a number, right? So if we have a pair of shoes, we have 2. If we got a dozen donuts, we got 12. If you got a gross, they used to say that with pencils. You got like 144 of them. So in chemistry, the word that we kind of use a lot is a mole. And first off, that is the actual abbreviation for a mole is MOL. They had to cut something off there. So they cut off the E. And it's really important to remember that when you do see MOL, it is actually the abbreviation for mole. It is not the abbreviation for molecules. So sometimes people get that confused, like they see the MOL and they just jump to molecules. It is actually just moles here. And a mole is basically the amount of substances that contain as many elementary entities like atoms, molecules as there is in the carbon-12 isotope. And I believe we talked about carbon-12 isotope. If you remember, that is the one they chose to get us all of our atomic masses that we find on the periodic table. So just like a pair of shoes and a dozen donuts, when you say you have a mole of something, it does actually represent a certain amount of it. And that number is, we'll come back to this, what is referred to as Avogadro's numbers. So 1 mole of anything is equal to Avogadro's number. So 1 mole of anything equals 6.022 times 10 to the 23. Now, the units that go with that number do vary depending on sort of what you're dealing with. They could be particles. They could be atoms. They could be molecules. It could be pizzas. It could be donuts. All right. So probably in chemistry, you're going to see pizzas and donuts a lot, but no, you will see here atoms and molecules are really the kind of 2 common units that we do see kind of used with Avogadro's number, which is the 6.022 times 10 to the 23. First off, you want to definitely make sure when you use that number that you are using your exponent button on your calculator. You definitely make sure you want to use that button correctly here. So what do we use this for? It is really, frankly, a conversion factor that we use. And it's a conversion factor to go from basically either moles to atoms or molecules or backwards. Atoms or molecules back to moles. And you can use it like dimensional analysis and as a conversion factor. You could say like a fraction, 1 mole up on top. Avogadro's number there on the bottom, or just like any other type of conversion factor, you could flip it around and put Avogadro's number up on top. You're kind of doing a dimensional analysis sort of deal, and 1 mole on the bottom here. So we really use it as a conversion factor to go between those 2 units. Now, people want to always use this number in every calculation because they're like, hey, I learned that number. Let me lay it down in everything I do. And you don't want to do that. So you only want to use Avogadro's number really in 2 situations. Either you have a number already given to you that's in atoms, molecules, something like that, which means you probably need to convert it to moles. Or you're asked to give an answer in like atoms, molecules, or something like that. Then you obviously need to use it on the back end of the calculation. If there frankly is no mention of any atoms, molecules anywhere in the problem, leave Avogadro's number at home. Don't use it. Yes. People sometimes use it at the beginning of the calculation, use it at the end of the calculation, which is a good thing because they multiply at the beginning, divide at the end, and they work out okay. But you don't want to use it. So we can apply this really to anything on the periodic table. So for example, if I have 1 mole of hydrogen, how many hydrogen atoms would that be? It would be 6.022 times 10 to the 23 atoms of hydrogen, as obviously hydrogen is an atom. You could even apply it to compounds as well. So, if I had 1 mole of water, I would have 6.022 times 10 to the 23 molecules of water. So on the top one, we use atoms because we're just talking about one element by itself, like hydrogen. On the bottom one, we're talking about water, which is a molecule. So we use molecules for the units there associated with Avogadro's number. And again, anybody on the periodic table, anything that's really a molecule or a compound, you could use all that relationship there. Any questions on that? Now, Avogadro's number represents, like I said, that number. And again, if you had 1 mole of methane, you would have 6.022 times 10 to the 23 molecules of methane. If you had 1 mole of iron, you would have 6.022 times 10 to the 23 atoms of iron. Obviously, you could write 2 conversion factors for each of those things. Now, the other sort of important, really conversion factor that we get from the periodic table that we use a lot, and honestly, we probably use it more than we use Avogadro's number calculations, and that is what is known as the molar mass. So the molar mass is a really important sort of number that we use to do some conversions. So let's talk a little bit about that. The molar mass is the mass in grams of 1 mole of a substance. And where do we find it? We find it in the exact same place that we find the atomic mass on the periodic table. So if we look at hydrogen, that number on the bottom, which is 1.008. Remember earlier, that was the atomic mass in units of AMU. Numerically equal to each other, molar mass has units of grams per mole. So those are the units associated with molar mass. The number always stays with the grams part, and it's always 1 mole. Now, grams per mole and the number that we see on the periodic table, which is AMU per atom, is numerically equal to each other. So if I take that number off the periodic table, that would tell me that there are 1.008 grams of hydrogen and a mole of hydrogen. And that means that the molar mass of hydrogen is 1.008 grams per mole. And we can use it as a conversion factor. We use molar mass to go from grams to moles and backwards, moles back to grams. That is the conversion factor that we use. We get it from the periodic table. If we had hydrogen there and we had oxygen, which is 16, and we had something like water, and we wanted the molar mass of water, we would take 2 times 1.008, which is the molar mass for hydrogen, and we would add it to 16 grams per mole, which is the molar mass of oxygen, and that would tell us that the molar mass of water is 18.02 grams per mole. Again, the number stays with the grams, and it's 1 mole. So the tying together of this and what we were talking about with Avogadro's number is there is 1.008 grams of hydrogen and 1 mole of hydrogen, which contains 6.022 times 10 to the 23 atoms of hydrogen. They're all sort of related to each other by that way. So if we look up there, 2299 for sodium, 6355 for copper, and that would be its molar mass grams per mole. Now, when you look at a periodic table and you go to get the molar mass from the bottom there, it is just like we talked about with atomic mass. It is usually 4 significant figures is usually what you take off of the periodic table. Again, depending on your periodic table, you may have a lot more numbers or a lot less numbers, but typically speaking, we do just take the 4 significant figures there as we go through it. Any questions on that? Yes. So they're numerically equal. They are numerically equal to value, but they are different units. And sometimes you would want to use sort of the different units for different applications. Most commonly, we use molar mass when we pull it off the periodic table, because if you think about it, when you're like in lab, for example, if you had to go weigh out something, right? If you probably have done that and you look on the scale, it's usually in units of grams, right? So that's a convenient unit that we use. There's not a lot of like scales and stuff that are like, this is, you know, how much AMU you're going to weigh out and stuff like that. So it's a more sort of convenient unit that we kind of use over the years than say maybe like an AMU per atom type of thing. Yeah. Other questions? That is also why I think I skipped a picture there. We'll go back it up real quick here. So when we look at each of these things, right, we do see different amounts in each of them. And a reminder that this is basically 1 mole of each of those things. Why is there different amounts in each of those guys? Yeah, so each of these represent basically 1 mole of each of these substances, like sulfur and iron and sodium chloride. And that's because when we take, for example, 1 mole of sulfur, right? If we go to the periodic table, that really represents like 3207 grams, right? If we take 1 mole of like sodium chloride, you add it together, that's 2299 plus 35, 45, that's like a 5844 maybe, yeah, grams. And that is why we do see different amounts in there. So a mole of sulfur represents a different amount than say a mole of copper or a mole of carbon and so forth. So they represent a different amount in sort of grams amount of it. And that's why, you know, some people would think, well, a mole of everything should look at about the same amount, but it does represent a different quantity in terms of grams. Any questions on that there? Okay, let's see here. So again, for the periodic table, you could pull any of those things off and get those relationships. So why don't we try some here? But again, we use Avogadro's number and really molar mass as conversion factors. And again, you can really kind of think of these type of calculations more like a dimensional analysis approach, and use either molar mass or Avogadro number as a conversion factor and get the units basically to sort of cancel out. So why don't we try one here? So how many moles of helium are there in 5.46 grams of helium? I'll give you some info if you don't have a periodic table. Helium is 4.003 is what it says. So why don't you take a moment here and see what you come up with? Okay, let's take a look. So first question is, do I need to use Avogadro's number here? I don't. Again, there's no mention of molecules or atoms, so we don't need to use Avogadro's number. We're really going from grams to moles. And to do that, that is the molar mass. That's our conversion factor to do that from the periodic table. Again, if we pull that off the periodic table, that is telling us we have 4.003 grams per mole that we could use as our conversion factor to do that. So we would start with our 5.46 grams of helium. And again, you can just treat it like a dimensional analysis. Grams are on top, which means grams need to go on the bottom to cancel. We're basically dividing. So 4.003 grams per mole of helium. Again, the grams will cancel each other. And we're going to take our 5.46 and divide it by 4.003. 3 gives us a 1.36 moles of helium in this case. Any questions on that there? And again, you can think of the molar mass as a conversion factor. You use it grams on top, moles on the bottom, or you could flip it and do moles on top and grams on the bottom. Let's try one more here. How about zinc? How many grams are there in 0.256 moles of zinc? Zinc is 6539, unless you get a fancy new periodic table. 39. Okay, so same idea here. We are looking for grams and we're starting with moles. So again, really no mention of atoms or molecules, so no need for Avogadro's number. Again, that is what we use our molar mass from the periodic table. Again, looking at that, that tells me that there are 6539 grams per mole is the molar mass of zinc. Starting with our 0.256 moles of zinc. Again, moles are on top in this case, which means we do want moles on the bottom and grams up on top. A reminder that, again, the number always stays with the grams and it's always 1 mole, no matter where you put it. And again, here the moles will cancel and looks like a 16.7 grams that would represent. Any question on those two there? Okay, I think we will lay it up there for like a week or so. Yes, sounds good.